Welcome back. We are nearly at the end. That's the good news. The bad news, we have to talk about time dependency, and that's the hardest thing. There's always a sting in the tail with these things, isn't there? So time dependency is the hardest concept. If you grasp it, you're absolutely sorted, and any sort of exam question will be a breeze. Otherwise, you may have to watch the video a couple of times, ask your mates, or send me an email, and I'll do my best to explain it with a different form of words. Okay? So, with that in mind, let's make a start. So what we haven't talked about so far is when we look at those rheological behaviours, you've got your graph. Let's say we're dealing with pseudoplastic flow. It's the easiest one for me to draw. Then we have a graph that looks like this. We apply a force to a material. That material changes in some way. So for a pseudoplastic material, we're breaking bonds, aren't we, that are holding that gum or paste together. And the material starts to flow more the higher the stress that we apply to it. It's a shear thinning material. And as a consequence, we get a graph that looks like this. The question is, what happens as we remove that stress? Everything we've talked about so far, I said we start at zero applied stress, and as a consequence, zero rate, and we increase the amount of stress that we apply. Increasing the stress, in this case, is breaking bonds. Breaking bonds means that the material flows faster, right? So the graph goes like this. What I never said is, well, what happens when we remove the stress and the material goes back to zero applied stress? If it goes like this, as we increase the stress, does it come back exactly along the same line as we remove that stress? Remember that the way the instrument is making these measurements is applying the stress, but it has to remove that stress again so we can take the sample out. Okay, so you think about the graphs that we've looked at already, so shear stress and the shear rate, and we get this sort of thing going on. All we've talked about is increasing the shear stress and the material thinning in this case. What happens if we remove that shear stress? Does the material come straight back down this line to the intercept, or does something else happen? Now, the fact that I'm asking you this question probably should tell you that something else happens. And the answer is, in the main, something does happen, yeah. And so it's about me explaining what this thing is that happens. And if you get it, then what happens to the rheological properties becomes kind of obvious. Okay. So the way to think about it is, imagine that we have a material undergoing plastic or pseudoplastic flow. So on the screen, there is the same picture as before, flocculated suspension with some polymer chains interlinking the particles. That's how the material is at the start of the experiment. We apply some force, some shear force to that material in order to make the measurement, and in applying that force we break the bonds, the intertangled polymer chains, we break those apart and the particles become separated. And because they're separated, they're able to flow much more easily, and the material becomes less viscous, shear thinning. That is what explains this part of the graph. So at this point, at the end of that graph, the material is thin. All of the chains have been broken apart and the material is thin and it's able to flow. The question is, what happens when we remove that force and effectively the material comes back down that line? Does it come exactly down that line? Are they mirror images of each other? Can we go backwards and forwards along that line, or does something else happen? So in this instance, you've got to remember that the reason the material thinned is because we broke bonds. Therefore, when we remove the force that the instrument is applying, if those bonds reform instantly, then the material will behave the same as shear is added or removed, because the way the material is changing in response to the force that's being applied is instantaneous, right? We're either adding a force and breaking bonds, or we're removing that force and the bonds are instantly reforming. If that happened, then we could go backwards and forwards along that line. They'd be on top of each other, and we wouldn't know whether the material was responding to an applied stress or a removal of stress. It's just instantly responding to the stress that's being applied. In reality, I think you might imagine where I'm going to head here. In reality, it takes a while for these bonds to reform. So the particles have been thinned, they're all whizzing around everywhere. We remove the force. It takes a while for those bonds to reform. because the particles have got to slow down. Imagine that you had a spinning top on a tabletop. You know, one of those things you had as a kid, and you sort of pumped it up and it spun around, spin, and then you remove your hand. Does it instantly stop spinning? No, because the material is carrying on moving after you've removed your force that you've applied to it. The material carries on spinning around, and it takes a while for it to lose that kinetic energy and go back to being at rest. The same principle applies here. You have got a system at rest at the start with lots of interparticulate bonds. You've applied a force and you've broken those bonds, and in order for the material to recover its initial starting position, those bonds have got to reform. And if those bonds take a while to reform, the material is going to behave differently once the force has been removed from when the force was being applied. So the question is, what happens to our rheological graphs if a material exhibits this time dependency? On the screen in front of you is the rheological profile for a pseudoplastic material showing a time dependency. You can see, without being an expert, this graph looks a little bit different from the one that we saw earlier. Principally, there are two lines on this graph, whereas before there was only one line. The reason that there are two lines is because the material is exhibiting a degree of hysteresis because of this time dependency. Now, I said already that interpreting these graphs, it's really helpful to talk your way through what is happening to the material, and never more so than in this case. I really do think that you need to talk your way through what this material is doing in order to interpret this graph. When we talk about this for real in a lecture theatre, obviously if I talk through it once and I ask, is everyone okay with that? You can put your hand up and you can say, sorry sir, I completely didn't get what you were saying there. Can we go through it again? And we'll go through it a number of times. But because you're watching this on a video, the best I can say is I'm going to try and explain it. If you're not following it, rewind this bit and watch it again. Or if you're still not following, we have one more example coming up with dilatant flow and time dependency. So watch that bit and see how you get on. Okay. So the basic principle here is, because this is a pseudoplastic flow, we have a rheological profile that looks like this. It's a curve, we saw that already. The viscosity of the material is the gradient of the line. The viscosity starts high. As we start to apply a shear force, the viscosity is getting lower. The material is shear thinning, and that's what we saw before. So the arrow on the top line is going in this direction. What it's saying to you is this is us increasing the shear stress. So it's what happens to the material as we increase the amount of shear stress that we're applying to it. The material starts to thin. When we get to the far side and we start to come back down again, that corresponds to the instrument taking away the shear stress, and it's going to go back to zero applied shear stress. And so that's what the arrow going in this direction is showing you. What happens to the material as you remove the shear stress? If there was no time dependency, in other words, if the bonds in this material reformed instantly, then what will happen is the line going in this direction is going to overlay the line going in this direction. It's a little bit like saying in the graphs we looked at earlier, there were actually two lines, but they're on top of each other. And so we didn't talk about them. It just appears to be one line. But actually there were two lines, up and down. They're just on top of each other. If there's a degree of hysteresis, those two lines start to separate. And that's what we see on the screen in front of us. The line on the way up shows you what happens as you apply stress. The line on the way down shows you what happens as you remove stress. Now, I've said this is a shear thinning material. So when I talk through this type of example, I think it's kind of helpful to hold that concept in your mind and talk to yourself about what you think the material has done. So the material is shear thinned. We applied a stress and the material is shear thinning. So the gradient of the line is getting lower. That means on the right hand side of the graph, the material is as thin as it is going to get. Because we've applied all this force, we've broken these bonds, and the material is free to flow around. When we remove that shear stress, if those bonds don't form instantaneously, then as we remove that stress, the material is going to be thinner on the way down as it was compared on the way up. So as we're applying the force to the material is starting to thin. On the way down, as we're removing that shear stress, the material remains thinner than it was at the start of the experiment. And that's the reason why these two lines are not on top of each other. If you need convincing that this must be true, pick any point on the graph. So I happen to have drawn an arrow at one particular point. So you can see an arrow coming across. So that arrow represents how the material is responding to one particular shear stress. You can draw an arrow anywhere that you like on the y-axis. Just draw the line across because it represents a particular shear stress that's being applied. As that line goes across your graph, the first of the data points it interacts with is what the material was doing as the shear stress was being applied. So in this instance, it hits the first line, the up line first. So if you draw an arrow down at that point, that shows you the shear rate. In other words, the rate at which the material is moving for that shear stress. Okay, doesn't matter what it is because you're just comparing the two lines. So the numbers don't matter. If you carry the line across until you hit the second line and you drop an arrow down to the x-axis, that tells you the rate the material is moving after the force has been applied and now it's being removed. I hope you can see from the graph in front of you that on the way up the material is flowing at a particular shear rate, doesn't matter what it is, but on the way down at the same shear stress the material is flowing faster because the shear rate is higher. So what that's saying is for the same shear stress that's being applied, on the way down the material is moving faster than it was on the way up. And the reason is because it's shear thinned. It's shear thinned because you've broken bonds and those bonds haven't reformed. And so the material remains thin. I think the easiest way of thinking about this is simply to say, I take a material which is being held together with some bonds, I apply some shear force to that material and break those bonds, and that makes it runny. And it remains runny until the bonds reform. That's the easiest way of thinking about it. But in a rheological experiment, it means that we get this curve on the way up and a slightly lower one on the way down, and we get this degree of hysteresis. I hope that kind of makes sense. Now, you might say to me, why are we talking about this, sir? Because materials don't actually act like this. And the answer is we are talking about it because materials do act like this. And I like to pick a particular example of a material that because let's face it, you're a lot younger than me. And so there's a particular material in your kitchen cupboard that you're going to add to almost any food substance to make it taste better that does actually behave that way. Can you think what that material might be? I'm going to give you just a second to think about it. It's got to be a semi-solid, doesn't it? What semi-solid in the kitchen do you add to everything? Yeah. So I live with two teenagers, and so they're upset right now because I've nicked this particular product from the kitchen cupboard. So the answer is tomato sauce. Tomato sauce is actually a time-dependent shear thinning material. Yeah, you never thought of that, did you? Right. Why do I say this, and what is happening? So the answer is, this is a material that does not flow very well. So you've got your chips, you want to put tomato sauce on it, so you turn the tomato sauce upside down. I was brave there, wasn't I? The material is not flowing, is it? The tomato sauce is here, my chips are here. I really want the tomato sauce on the chips, and right now they're not flowing. What do I do to tomato sauce to get it to flow? I'm sure you're a very competent tomato sauce user, and I have made very sure the lid is on before I do this. We do this, don't we? Okay, now what will happen is, if I take the lid off, and I'm not going to because my computer's really expensive and it's not a bowl of chips, but if I were to take the lid off right now, the material is going to flow out of here onto my chips. The reason is because in doing this, I'm effectively adding a shear force to the material. That is breaking apart the bonds that are holding the tomato sauce together, and it's making the material flow. And because it's a time dependency, the bonds don't reform instantly, and so I can shake it and the material is now flowing straight afterwards. This sort of behaviour does also apply to almost all pastes, gums and flocculated suspensions, by the way. It's just that tomato sauce is a very handy example for me to demonstrate. Now, I said, what happens if you're not following this time dependency? Rewind that bit and watch it again. Or I said we'll talk about it again with a different example. So on the screen is the time dependent graph for dilatant flow. Okay, the same principles apply here as earlier. There are now two lines on this graph compared with the one on the graph that we looked at earlier. The basic graph is the same, obviously. It's showing shear thickening. So this is a shear thickening material. So what that means is the arrow going in this direction shows you what's happening to the material as you start to apply the stress, and so the material is starting to thicken. So it's doing this, the gradient is getting steeper, and that was because we were applying a force, the particles were clumping together and they were losing the lubricity of the continuous phase between them, so they were becoming a lot harder to move. So when we get to the top of that graph and we start to remove the force and we come back down again, if those particles instantly start to come apart, then the material will go backwards and forwards on this line and we'll only see one line. But if it takes a while for the particles to come apart and the continuous phase to start to re-lubricate between those particles, then the material is going to remain thicker. So we apply a force, the material gets thicker. As we remove that force, the material remains thick. In other words, we put some energy into it to thicken the material, and even though we stop adding that energy, the material remains thicker than it was before. A consequence of that is you need to convince yourself this is true by drawing arrows again. So, as before, there is a horizontal arrow on the graph for any particular stress, and you can choose any other one, you don't have to use mine, doesn't matter what it is. Follow where the arrow goes across until it hits the line on the way up as you're applying the stress. Drop an arrow to the x-axis and you'll see that's the shear rate that the material is moving at as we are applying the force. Do the same thing, drop the arrow down when you get to the line, on the way down, so that's on the way down, and you'll see that after you've applied the stress and then removed it, the material is moving more slowly than it was on the way up because the material has got thicker. So on the way up, the material is moving relatively fast, it goes up, it comes back down again, you remove that force, the material is now moving with a lower rate because the material is thicker, and so it's going to move less for the same applied force. Okay, so in other words, this is a shear thickening material that remains thick after you've applied a force to it. Are there pharmaceutical examples of materials that behave this way, sir? I hear you ask, and the answer is not many actually, but one is shaving foam. I tried to go around this house and find some shaving foam, and as you can see, I haven't got much. So there's a picture of it on the screen, and the way this would work, obviously, is you take the shaving foam, you squeeze it into your hand, and you apply, and it's quite runny, isn't it? It's quite runny as you apply it into your hand. You then apply a force by shaking your hands together, and you get this big foam, and it's a lot thicker. It flows a lot less once you've applied that energy. So that is an example of a shear thickening material, and it remains thick actually. So you apply that force, it remains thick enough that you can cover your face with it. The other picture on here, you might say to me, sir, there's a picture of a horse at the end of your lecture, and this is a pharmaceutical lecture, and I would say yes, I can't argue with that. There is actually a picture of a horse at the end of this lecture. Why? The answer is the horse is stuck in quicksand. And quicksand is a really classic example of a material that shows time-dependent shear thickening. Oh, I should have said actually that time-dependent shear thinning is given a special name. It's called thixotropy, and time-dependent shear thickening is given a special name. It's called rheopexy. It was written on the slides, but I didn't say it actually. So quicksand is a classic rheopexic material. What is quicksand? That's a good question. It's a suspension of sand, concentrated sand, in water. So in other words, it's a concentrated deflocculated suspension. It's funny, isn't it? That's what the example we looked at earlier. Yeah. So what will happen with quicksand is you've got lots of water in between the particles of sand, grains of sand actually. And so when you walk on it, you can start to sink into the material because it's basically a really viscous liquid. And so you'll drop down into it as the horse has done. Now, should you ever find yourself in quicksand, I'm going to give you some advice of how to get out of it. Think of me like the pharmaceutical example of Bear Grylls. Okay, so what you need to do if you're in quicksand is not move. It's completely understandable that if you dropped into quicksand, the first thing that you do is start flailing your arms and your legs around because you're starting to panic. Panic, panic, panic. Remember, quicksand is a shear thickening material. As you're flailing your arms around and your legs around, you are applying energy to that material. What you're effectively doing is making the sand, grains of sand, start to come together and they lose that lubricity. And if you do that, you'll actually set the quicksand like concrete. The number one reason why people die in quicksand is because they try really hard to get out and they actually set themselves into a concrete-like material and they've got no chance of getting out. until they stop moving and the material relaxes, but it can take quite a long time for it to relax. And especially in an example like this, because quicksand is usually found in and around beaches, you can set yourself in quicksand and then the tide comes in and you can't get out. It's a disaster. So the thing to do with quicksand is to move really, really slowly because it's a shear thickening material. So should you ever find yourself in quicksand, and you can see videos where Bear Grylls gets himself out of this type of situation, you just need to move really slowly to get yourself out of the situation. And you'll be pleased to know that they did rescue that horse from the quicksand before the tide came in, so I did check that. There is one other really classic example of a material which behaves this way. Well, two really. One is silly putty, if you ever played with that. So that's that sort of putty where you can squeeze it and mould it a bit like blue tack. But if you make it into a ball and you throw it at the wall, it suddenly bounces back at you. And the reason is because when you throw it at the wall, as it hits the wall, you've got a really sudden amount of energy being applied to that material and it sets solid. And so it goes from being a more liquid-like material to almost an elastic solid as it hits the wall, and that's why it bounces back and hits you in the face. And the other one is corn flour in water. You may have seen some videos like this, and I might even put a link to a YouTube video you can watch, which was from the series Mythbusters, where they filled a swimming pool with corn flour in water. So that's very similar to quicksand, and you can run across it if you run fast, because as you're running you're applying a lot of force very quickly. The material becomes very hard, but as soon as you stop then you'll sink into it. So there's a video you can watch where the presenter runs across corn flour in water and it's fine, but he runs across and then stops in the middle and then sinks into it because it's not fine. Right, you'll be pleased to know that is the end of the lecture. So on the screen is the summary, what you need to remember, which I shall summarise like this. Rheology is the study of the deformation and flow of material, and we characterise that by viscosity. Viscosity is the resistance to flow. The higher the viscosity, the harder it is to get a material to move. It's very important in understanding, characterising and indeed formulating various pharmaceutical products. Usually creams, suspensions, ointments, pastes, things like that. Things that are semi-solid. And the rheological properties are absolutely key to the way that the consumer interacts with that product. Remember my cream from earlier that I was rubbing onto my hand. How do we characterise rheological properties? We plot shear stress versus shear rate diagrams. If the material is a Newtonian fluid, then the shear stress versus shear rate diagram will be a straight line and the viscosity will be constant. If the material is not a Newtonian fluid, the shear rate, shear stress diagram will not be linear and the viscosity will constantly change. If the gradient of the line to the viscosity is reducing as the shear stress is applied, the material is shear thinning. From a pharmaceutical perspective, shear thinning materials exhibit plastic or pseudoplastic behaviour. If there's a yield point, the material is a true plastic, and more likely there's no yield point, the material is a pseudoplastic. If the gradient of the line is getting steeper and so the material is thickening, it's becoming a shear thickening material. That's a dilatant material, and that is usually associated with concentrated suspensions where you're losing the lubricity of the continuous phase. And the final thing to remember is that in all of these plots you are always adding and then removing energy. If the material responds instantly to that addition or removal of stress, then effectively you've got two lines on top of each other, so they just look like one line. But if the material takes time to respond to the change that you've caused because of the input of stress, the material is going to exhibit a time dependency. If it's a plastic or pseudoplastic material and there's a time dependency, the material is thixotropic. And if it's a dilatant material with time dependency, the material is rheopexic. Right, we are done. I hope that's okay. I hope it made sense. If it didn't, you're completely free to send me an email. Otherwise, I will see you next year.